All right, this is going to be page 1 of notes 13 of Calc AB, and we are going to be talking about antiderivatives, which is something that's we're going to end up using them all the time. It's a really, really big idea. In fact, you might say it's a huge concept. We've encountered it a little bit before. So when we were talking about velocity, acceleration, and position, so position, velocity, acceleration, really in that order, we kind of decided that if we could work out how to do it, we could go from an acceleration function to a velocity function. If we could work out how to do it, we could go from a velocity function to a position function. We were finding antiderivatives, right? You take the derivative of a function to get its derivative. If you have its derivative, how do you reverse that? You take an antiderivative or an integral. So when I was learning calculus, I just called them integrals all the time, so I'm probably still going to do that. So there's some notation. They look a lot like the definite integrals that we've been doing in the previous notes. They don't have any bounds. There's nothing there. So these are also called indefinite integrals. Definite integrals have bounds in their numbers. Indefinite integrals, the result is a function of some sort. Two different notations that you'll see for them. So I prefer this notation. So if you find the antiderivative of f prime of x, it makes sense that you would just get f of x back, right? Because you're reversing, taking the derivative, you're going from the derivative to the original function. So f prime becomes f. The problem is, and we've seen this, that the derivative of a constant, so d dx of a constant is equal to 0. So when we find an antiderivative, there's no way to know what constant was hanging out at the back of your function. So what we do is we just put a plus c. So many memes about that. So you'll see it frequently. It's like a really common AP exam, like, oh, I did all this and then I forgot plus c. Plus c is super important. So we got to put it every time. Let me highlight that in red. Plus c, that's supposed to be red. It's definitely red, like it's the reddest color on the palette, but whatever. Another very common notation, which I hate because there's no easy way to say it, is the integral, the antiderivative of like lowercase f of x, I don't know, is capital F of x plus c. So this is really common also. You'll see it for sure. I tend not to use it if I can avoid it because I think it's kind of a confusing notation and mostly because it's really hard to talk about. So what we want to do is see if we can work out some antiderivatives. So we're saying this is the derivative of something. Well, if I look at that, that looks like the derivative of lots and lots of power functions. It looks like somebody just went through and power ruled this entire polynomial. So we want to reverse that. So what I'm going to do, I'm going to kind of ask myself, what did I take the derivative of to get 5x to the 4th? Well, that's clearly the power rule being used, I think, on x to the 5th. So for some reason, my page moved when I wrote that. So I think that is x to the 5th. I think that 4x cubed comes from taking the derivative of x to the 4th. I think 3x squared comes from taking the derivative of x cubed. 2x, I think, comes from x squared. And then 1 is the derivative of x. So I'm going to say that with x, but then plus c. This is how we can find an antiderivative. Now, what happened here? So in each case, so I don't know how I'm going to highlight this. We went from 5, and then this became 5. But that's not necessarily really what happened. I'm going to say what really happened is that I did, so this is, I'm going to show like weirder work this time. So we had 5. And then I'm going to say I multiplied by 1/5, and then x to the 4 plus 1. I added 1 to the exponent and multiplied by the reciprocal of that. So this is 1 to the exponent. This is the reciprocal of that. And then there's just a 4. It's like a constant multiple. I got 1 over, maybe I'll write it as 3 plus 1, and then x to the 3 plus 1. So this, add 1 to the exponent, multiply by the reciprocal of that. And then it canceled with the 4, it canceled with the 5. It's going to do that all the way through. So there was the 3, and then I'm going to say 1 over 2 plus 1, x to the 2 plus 1. I feel pretty committed to doing this all the way through now. I'm not enjoying it, but I'm going to keep going anyway. So in each case, what I was really doing was focusing on the x to a power, the power function, adding 1 to the exponent, multiplying by the reciprocal. And like maybe you would work that out, but in my experience, some people don't. So there's 2, 1 over 1 plus 1, x to the 1 plus 1. I added 1 to the exponent, multiplied by the reciprocal. It happened to cancel with the 2. You know, if it doesn't, it doesn't. Not really a big deal. And then plus 1. 1 over 0 plus 1. So this one's weird. X to the 0 plus 1. So I still added 1 to the exponent and multiplied by the reciprocal. It just like, that's a weird one, but it works. And then plus c. I'm gonna move this over so it's not in the way. And then I'm gonna try the next one. So the next one is another like pretty straightforward one, but you'll notice the coefficients are like a little bit off, right? So if the derivative of something is x to the 7th, then that thing was probably x to the 8th, because the power rule, you bring the exponent down, subtract 1. But there's no 8 in front of this. So what that tells me is that there must have been a 1/8 in front of it to begin with. So let me just start by finding this. So I'm going to do, I'm looking at the 7. So it's going to end up x to the 8th, add 1, and then the reciprocal of that, 1/8 x to the 8th. Take the derivative, right? So you bring the exponent down, 8 times 1/8 is 1, and then x to the 7th, this works. So plus 1 times the reciprocal seems to work. So I'm going to do it again. The exponent is 5, so it'll become 1/6 x to the 6th. You can always check your antiderivatives by immediately taking the derivative. And I kind of recommend that you do that. So this will be 1/5 x to the 5th. And then here, the current exponent is 1, add 1, that's 2. The reciprocal is 1/2, and then x to the 2nd. 9 is the derivative of 9x, and then we say plus c. So we're doing plus 1 times the reciprocal. I basically say it all the time. Plus 1 times the reciprocal. Reciprocal? Probably. Okay, plus 1 times the reciprocal. That's how we're going to reverse the power rule. So let's look at this. Same idea, but now it's a little more messed up. So we employ the constant multiple rule all the time. That 3, whatever, just ignore it until you figured out what to do. So 3, now deal with x to the 4th, plus 1 times the reciprocal. So that's going to be 1/5 x to the 5th. And then the 7 is a constant multiple. Ignore it. Reverse the power rule on x cubed. Plus 1 times the reciprocal. It's going to be 1/4 x to the 4th. 6, we ignore it. Plus 1 times the reciprocal. The -10, we ignore it. Plus 1 times the reciprocal. And then 8x. Then we do plus c. Now, once you do a bunch of these, you're going to kind of skip this step and jump right to what I'm about to write, because it's easy enough to keep track of in your head. So this is really 3/5 x to the 5th plus 7/4 x to the 4th. 6 over 3 is 2. X cubed minus 10 over 2 is 5. X squared plus 8x plus c. Plus 1 times the reciprocal. You want to check it? Go through in power rule. Bring the 5 down. 3/5 times 5 is 3. And then x to the 4th. Bring the 4 down, you get 7x cubed. Bring the 3 down, you get 6x squared. Bring the 2 down, you get -10x. The derivative of this is 8. It worked. So let's see, how many of these are there? We're good. Let's just do it. All right, so when in doubt, just show more work. When not in doubt, go for it. Check it by taking derivatives. So I'm going to pull the 3/2 out. If I add 1 to this, I get 3/2, right? So 1/2 plus 2/2, 3/2. Reciprocal is 2/3 x to the 3/2. And then pull the 4/5 out. So is this one perfect, just in disguise? I think so. -1/5 plus 5/5 is 4/5. Reciprocal is 5/4. X to the 4/5. And then 7/4. If I add 1 to this, trick question. They don't all just work out. 7/4. So if I add 1 to 5/4, that's 9/4. So 4/9 x to the 9/4 and plus c. Then when we simplify, a lot of it's really nice. X to the 3/2 plus x to the 4/5 plus gross 7/9 x to the 9/4 plus c. Plus 1 times the reciprocal. Can't really stress it enough. Let's highlight it again. Well, let's highlight it the first time. Plus 1 times the reciprocal. We're going to do that. And you just ignore constant multiples if they're in the way. If you can combine them like quickly, do it. If not, you know, pull them out, work with it. You might recall taking derivatives that radicals are kind of the enemy of getting answers correct. Basically the same thing. Doesn't this look like it's formatted funny? Like this looks like it's way higher than it's supposed to be. I don't really know why. Whatever. Radicals are bad. So before I even do anything, I'm going to rewrite this as x to the 1/2 plus x to the 1/3 plus x to the 5/4. And now we're just reversing the power rule. Reversing the power rule, I think, actually has a name. I don't know what it is. It's like named after a person or something. I tried to like look it up once on Wikipedia, and I think I found an article. I was like, I don't know if this is something that really needs a name, because reversing the power rule seems pretty good. 4/3, and then 9. You know, it turns out that I don't like adding 4 to 5. Every time I get to that, it's like I have like a mental block, and like I get nervous. Like, oh, am I going to do it correctly? So if you want to check your answer, take derivatives, right? So here, the 4/9 and the 9/4, that's good, that's gone. Subtract 1, you get 5/4. Rewrite it as a radical. Here you just bring it down. Subtract 1, you get to the 1/3. Bring it down. Subtract 1, you get to the 1/2. So looking good. Not forgetting plus c. It's essential. All of them. Never forget plus c. That's like such a rookie mistake. It's not even a rookie mistake. It's such a like careless error. All right, 3, 5. So 5/3. So 3/5 x to the 5/3. So notice I don't want to simplify in my head, so I'm just writing down the constant multiple, and then I'll deal with it when I deal with it. 3/8 x to 8/3. And then plus, whoa, where are you going? Plus c. So now we can simplify. 18/5 x to the 5/3 minus 3/2 x to the 8/3 plus c. And we can check it by taking the derivative. So if I multiply 5/3 and 18/5, I get 18/3 is 6. X to the subtract 1 is 2/3. That's good. If I bring down 8/3, I get -4. And if I subtract 1, what am I doing? Oh yeah, subtract 1 and I get 5/3, and that works. So key thing here is we can do this. And I always say it out in words. I say plus 1 times the reciprocal. So if the exponent is n, you do n plus 1 times the reciprocal. Not going to work if n is -1. And there's a reason for that. And we actually know the reason for that. So the derivative of the natural log of x, you might recall, hopefully, is 1/x, as long as x is greater than 0. So this power rule does not work on. If we have to do the integral of 1/x dx, we're actually going to get, for reasons we'll talk about, the natural log of the absolute value of x plus c. So it does not work for n equals -1. Literally every other value. It could be pi, x to the pi, right? If we integrate x to the pi dx, we're going to get 1/pi plus 1 x to the pi plus 1 plus c. That's it. Did I forget plus c? I did not. Whew, I did not forget plus c. Nice. Okay, so I'm going to cut this video here. I'll be back in the next one to do some more. So that's reversing the power rule. It's like your #1 strategy is to be able to reverse the power rule. So get good at that. I'll see you in the next video.